So what I've did up till now is I told you what a task is. It's this triple of two complexes and a carrier map between them. But I haven't said anything about what it means to solve such a task. So we're going to solve a task with a program that we'll call a protocol. And we're going to assume a kind of a normal form for protocols. That is, we're going to assume that everything looks like this program here. So we start out, this is a finite program. The loop is bounded. There are no circumstances under which it runs forever, and that's important. So you start out with your input value. A process starts out with some kind of input. It could be consensus, it could be case set agreement, it could be renaming any of these other tasks. But you start out with something that you yourself know as your private state. Then you run for a fixed number of rounds. And this number might be a factor of a function of the number of other processes and so on. But there's an upper bound on how long you run. The first thing you do is you send your current state to everyone. So this is a full information protocol. Here, when I say broadcast, I'm thinking of message passing system. But if it's shared memory, you could be writing to a shared memory. You could be doing any kind of communication. But you're basically telling everyone, this is how I see the world right now.
So even if you're allowed to send only to some of them, you choose to send to all of them?
Yes. Yeah, because we're not going to worry right now about message complexity or the number of bits. Everything here is exponential. And because a lot of what we're going to prove are lower bounds, impossibility results, and so on, we're saying that even if I can send you exponential size messages, you still can't solve the problem, or you still can't solve the problem in a fixed certain amount of time, and so on. So if you wanted to do this in a more practical way, you would think, well, I don't need to send all the bits. But for now, we assume that you just send your entire state to everyone all the time. There's no randomization. There are lots of interesting things to say about randomization. Almost everything I'm going to tell you that's impossible is possible with randomization. So, but this is all deterministic. So then you take everyone else's view and you concatenate it to your view because now you sort of know more about the world. And then you go around and you do it again for a certain number of times. And then in the end, after running for a certain amount of time, you've concatenated everybody's view of everything. And so far, what I've described is completely generic. I haven't said anything about what problem you're trying to solve. So at the end, you look at the state that you've established, and you say, oh, based on this, I'm going to decide 1 or something else. And we're going to hide all of that in this decision map we call little delta. So this is where all of the problem task-specific machinery is hidden, is in this function that says that I look at everything that happened. Maybe it's exponentially more bits than I need. And based on that, I'm going to compute my answer. So this is our notion of what a protocol is. And it will change a little bit when we talk about shared memory, black box memory, and so on. But this is the basic idea. So if simplicial complexes are good for inputs and outputs, then they must also be good for describing protocols, for describing program executions. So protocol complex is going to be a big, complicated simplicial complex. Each vertex is labeled with a process ID and the final view. That is, after running this full information protocol and building up all the information, this huge state that you've accumulated, we're going to label the vertex with that.
So you assume, in addition to the initial input, they all have unique IDs.
Yeah, everybody has unique ID, and in fact, we're going to assume it's between 0 and n most of the time, except when it's interesting to relax that. Simplex is just a compatible set of views. And by compatible, I mean that there was one execution where these were the views that everyone saw. So you could have, there could be more than one execution can produce the same simplex if nobody can observe the difference. So let's look at a concrete example. Let's imagine a very simple synchronous system where everybody broadcasts their state to everyone else on fixed rounds. So there's no funny business with timing. Everybody just broadcasts their state to everyone else. You collect all the messages, and then you rebroadcast everything to everyone else. The one thing that makes it interesting is that if a process crashes, it might do a partial broadcast. So it could send no messages, it could send one message, it could send messages to everyone, it could send messages to an arbitrary subset. We don't know. So that if you crash, then some people might know in the same round if you don't send them a message, but everyone will know in the subsequent round. So let's think about a binary consensus protocol in this model. So one possible way to start is everybody has a 0. So this is a simplex of our input complex, where represents the initial state where everybody has 0. It also represents the protocol complex after nothing has happened. So this is after sending 0 messages. If everyone starts with 0, this is what they know, which is basically only their input. So no messages are sent. Everybody's view is just its input value. And it's actually the same as an input simplex. And so as we saw before, if we put all the possibilities together, this is the round 0 protocol complex, which is actually, of course, isomorphic to the input complex. So now things get interesting when we do something. So say what can happen. Let's say that we're only allowed to have one failure per round, just to keep things simple. So claim is if you, after one round of computation, if you start out in a state where everyone has a 0, then this kind of Pythagorean-looking complex is a set of all possible states after one round of this execution. So what does it say? Well, the solid triangle represents an execution where no one fails. Everybody sends their messages to everyone else. Each of these squares, so this represents an execution where the blue process fails. So there's no blue vertex here because when a process fails, we throw out its vertex because we don't care about it anymore. So here, the green process gets a message from everyone. So blue sent a message here, then it dropped dead. Here, blue crashed before it sent a message to red. The edge between them says that there is some execution where green does get a message from blue, but red does not. And then here's the execution where blue fails without sending a message to anyone. And here's an execution where blue sends a message to everyone and then dies after sending those messages. And so here, for example, red does get a message from blue, but it doesn't know whether there was no failure, whether in fact blue failed, or whether in fact green failed. So if we put these together, these are all the executions in which 0 or 1 processes fail. So if we put the whole thing together and look at all the possible executions from all the possible initial states, you get a complex that looks like this. So this is the protocol complex for a one-round synchronous message passing protocol in which 0 or 1 processes can fail on each round. So again, I want to emphasize the idea that each triangle and edge here represents one possible computation. So we have this static geometric or combinatorial object that represents all possible interleavings, all possible failure patterns in one static thing. And we can talk about it as a single static thing instead of talking about what now this happens and now that happens and so on. So it's combinatorial rather than operational reasoning. We run for another round, it looks like this. And after that, it's not terribly interesting. So we put it together. You can see kind of a pattern here. So after 0 rounds, we have this. After 1 round, we have this. And after 2 rounds, we have this as our protocol complex. Now, there are a couple of things that we'll investigate in more detail. But you can see you start out with kind of a sphere. You end up with something that has holes, but it's connected. And then it becomes disconnected after a while. So here is our sort of model expanded to talk about protocols. So the task is given by an input complex, which talks about all the possible initial states, an output complex, which talks about all the possible final states, a carrier map that says if you start out here, here are the places you can end up. We have a protocol complex you can think of as an operator that takes the input complex and turns it into a protocol complex. And what do you do after you run your protocol? Well, you look at your state and you choose a vertex on the output complex. So it turns out that we can represent this as this small delta map that takes each vertex from the protocol complex and maps it onto a vertex in the output complex. So I look at my state and I decide a value. Well, that's actually just that's a vertex map. Well, in fact, it's more than a vertex map. It's a simplicial map. Because if you think about it, each simplex in the protocol complex represents a final global state. Each simplex in the output complex represents the decision values in some global state. And so all of the different decisions that each process makes in the end, they had better be compatible with each other, which means that you have to map a simplex to a simplex. So this is a simplicial map. So it actually preserves a lot of the structure of the protocol complex when you map it onto the output complex. So our basic strategy for lower bounds is very simple. You know, the mechanisms and arguments that were used to do this will take up most of the semester. But the basic idea is we'll find what's called a topological obstruction to this map. That is, we'll find some combinatorial topological reason why this map cannot possibly exist. And that's the basis for doing nearly all of our lower bounds. That there are because simplicial maps preserve so much structure, you can show that it's not possible for a simplicial map to go from here to there because in some sense the structures are too different. You know, and this is something that topological methods are very good at. Actually, doing algorithms will be a little bit less cumbersome, but the lower bounds are much easier. So let's do I'm going to do a very hand-wavy example of what this kind of proof looks like. We'll do this proof several times much more rigorously later on in the semester. But right now, I'm going to give you the hand is quicker than the eye version of it. I'm going to pull coins from behind people's ears in this proof. So here we have our protocol complex for the one-round execution. And I want to convince you that you cannot solve consensus with a one-round protocol in this context. And I'll mention as an aside, this result here is actually the direct descendant of a paper that Shmuel and his friends wrote back in some time ago. Okay. Okay. Okay, so if you remember what this looks like, these represent all the executions that can happen if everyone starts out with a 0. And we know that everything there has to map here. Because if you start out with all zeros, you have to decide a 0. Symmetrically, the piece of the complex that represents executions where everyone starts out with a 1 is at the sort of opposite side of the complex. And that, of course, has to map there. So natural question to ask, have to work on the animation here. So let's take this and notice that you can take a path. I can take a vertex in the all 0 region, and I can find an edge path that goes to the all 1, connecting these two things. And what I know is that the path, if I start at 0 and go to 1, that the beginning of the path has to start out here because it goes to all zeros. And the end of the path has to end up here. So I'm looking at the image of this path under this simplicial map delta. One end of the path has to go here, and one end of the path has to go here. Now, does anyone see a problem with this? So you can think of a simplicial map as a continuous map. Then what's the problem with having a path that goes from one triangle to another one when the two are disconnected? Well, you can't have a continuous image of a path linking two things that aren't connected. So one way to think about this is to say, well, this is the obstruction. Think of this as a zero-dimensional hole that separates these two things. That the fact that these things are disconnected, that there's no path between them, is an obstruction to making a path between them. And in a kind of a hand-wavy way, this is the proof that the one-round protocol does not do a consensus, because we know we can build a path over there from the all-zero, but we can't build the path over here. So this is kind of the flavor of a lot of the proofs that we'll do. So the conjecture here is that a protocol can't solve consensus if its protocol complex is path connected. And you know, as I said, we'll do this more rigorously later on, but you know, really you understand the proof just by looking at these pictures. Now, interesting thing is that you know, the proof is actually model independent. So all I'm saying is I have this protocol complex object, and I have the output. And if I can draw a path on the protocol complex object, then I don't care what the timing model is. I don't care what the failure model is, because all of that has already gone into the mix to give me my simplicial complex. All I have here is this simplicial complex. If it's path connected, then I have a model independent result saying under these circumstances you cannot solve a consensus. Now, if you I care about what the failure model is when I create this complex. But once I've once I put it in the oven and taken out the complex, then the argument is completely independent. It's a purely combinatorial topological argument. So this is what I mean when I said earlier that I want to separate the model-specific reasoning from the general property. So this is the general property. And if I want to prove that I have some very esoteric model of computation in which clocks have this property and failures have that property, then all of that goes into constructing the complex. Once I construct the complex, I don't care about that anymore. But what I have to prove now is, to apply this, is a general statement about the complex itself. And I don't need to entangle this kind of reason. I don't need to entangle the model-specific reasoning with this kind of reasoning. So this is the level of generality of that that we want. Yes?
The fact that once complex is path connected, is connected to the model. I mean, can it be path connected in one model and not?
Yes. No. That part is whether it's connected or not. It does depend on the model, but the fact that all you need to worry about is path connectivity is model independent. So this is the separation that I've been looking for. So if the adversary can keep the protocol complex path connected forever, so remember we had adversaries that will control failures. So what I showed you is a result for a specific protocol. It says this protocol cannot solve consensus, the one-round protocol in this failure model. But I say, well, now let me look at the family of all the protocols that are possible in a given model. If the adversary can make sure that every single one of them is path connected, that means that consensus cannot be solved in that model by any protocol whatsoever. And this is usually true of asynchronous models, where the adversary can stretch things and so on and guarantee that any protocol you write, no matter how long it runs, will always remain connected, and therefore you can't do consensus. So this is a class of models where consensus just can't be done, period. Now suppose I have something where the adversary can keep your protocol complex connected for a fixed number of rounds. So this is typical of synchronous models. So you remember, if you remember those pictures, you know, the protocol complex started out, you know, it was an octahedron, then it's connected, then becomes disconnected. At the point it becomes disconnected, you can actually solve consensus. So this gives you a round complexity lower bound in these models. And we'll also look at the semi-synchronous model a little bit, where you can have, we have bounds, and there that gives you a time complexity lower bound. So this is an example of the way where you can use a very general topological result in a fairly kind of abstract static model. You can apply it to a whole range of different computational models, a lot of those dots in that cross product I looked at earlier, and you'll get model appropriate bounds. But you get I think a nice separation between kind of the general principle, which is in this case path connectivity, and the model specific results. So I'm almost done. Here's another conjecture. So you remember we generalized consensus to case-state agreement. So I told you you can't do consensus in if the protocol complex is path connected, that is, if it has no zero-dimensional holes. So here's an even wilder conjecture, which says that you cannot do case-state agreement if your complex has no holes in dimension less than k. And of course, I haven't told you what a hole is. We will, but this seems like a natural generalization for some value of these terms. And in fact, this is one of the things that we'll do. We'll do this several times, in fact. We'll do some simple cases of this and then general cases. But this is another case where once you put in all the model-specific ingredients, you pull out the complex. What determines whether or not you can solve this case-state agreement problem is a purely topological property of the protocol complex, and not something where you don't need to mix reasoning about timing and failures and so on with this kind of a property. All of that has been worked out. So that's what I'll do next time is I'll take this and start doing it in a more serious way. And we'll get down and actually look at some specific, we'll start with some specific models, improve some results, and then generalize to other things. Okay, so next week.